Most people think the centre of our galaxy is something distant and abstract. A point of light too far away to matter. 26,000 light-years. A number so large it stops meaning anything. That distance is exactly why nobody's worried. It is too far. Whatever happens, there stays there. The galactic centre is not your problem. Except, that is not what the data says. For 15 years, something has been leaving the galactic centre and moving outward through the Milky Way. Massive, energetic, confirmed by 4 separate space telescopes and dozens of ground-based observatories. No origin story, no consensus on mechanism, and no clear answer to the question that matters most: what happens when it keeps going? Researchers studying this have used words they do not normally use, words like unexpected, anomalous, puzzling. In a scientific paper, those words mean something specific. They mean the standard model did not predict this. They mean the current theory does not fit. The galactic centre has been sending something outward for at least 8 million years. You're inside the Milky Way, you're downstream, and what is coming from the galactic centre has been travelling in your direction for longer than our species has existed. If this kind of content keeps you up thinking, subscribe. It helps more than you know. Now, let's begin. The galaxy hides its centre behind 26,000 light-years of its own wreckage. You cannot look at the galactic centre with your eyes. This is not a matter of telescope power or atmospheric interference. The obstacle is structural and total. Between the Sun and Sagittarius A, the supermassive black hole anchoring the centre of the Milky Way, lies 26,000 light-years of gas, dust, stellar remnants, and molecular debris so densely packed that the visible light from the galactic core is completely absorbed before it reaches us. It does not arrive faint. It does not arrive filtered or dimmed. It does not arrive at all. If you pointed the most powerful optical telescope ever built directly at the galactic centre tonight and stared for 1,000 years, you would see nothing of what is actually happening there. The signal is extinguished. This is why the galactic centre spent most of human history as a mystery hiding in plain sight. Ancient cultures noticed that the Milky Way was brighter in one direction, thickening toward the constellation we now call Sagittarius. They built myths around that concentrated glow. Egyptian astronomers observed it. Polynesian navigators used the Milky Way structure for orientation. But what was producing that brightness? What was physically happening at the centre of the spiral structure we call home was invisible to every human eye that ever looked upward until the 20th century. Completely sealed. Behind a wall we could not see through and could not remove. What broke through that wall was not better optics or larger mirrors. It was a different kind of light. Radio waves pass through interstellar dust the way a broadcast signal passes through the walls of a building. They operate at much longer wavelengths than visible light, typically millimeters to meters, and the dust particles that block optical photons are simply too small to interact with radiation at those wavelengths. The geometry does not match. In 1974, 2 radio astronomers at the National Radio Astronomy Observatory, Bruce Ballack and Robert Brown, were conducting a systematic survey of the galactic centre region using a radio interferometer when they detected a compact, anomalously bright radio source embedded in the broader diffuse emission of the galactic centre region. The source was small, point-like by the standards of the instruments available, and far more radioluminous than its surroundings in a way that suggested something unusual was happening there. They designated it Sagittarius A, the A for the first compact source identified in that region. Subsequent observations at higher resolution divided this region into subcomponents, and the innermost compact object came to be called Sagittarius A. The asterisk pronounced star by convention to mark it as the special central designation. That asterisk was earned. The compact radio source Balick and Brown had found in 1974 would be confirmed over the following decades, through increasingly precise measurements by increasingly capable instruments, as a supermassive black hole containing approximately 4 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury. But radio waves were only the first key to unlocking the galactic centre. Each different type of electromagnetic radiation opened a new window onto a different physical process happening there. X-ray telescopes launched into orbit above Earth's atmosphere, where the atmosphere's absorption of X-rays would otherwise block detection entirely, revealed hot gas at temperatures of millions of degrees, energetic outflows moving at high velocity, X-ray binary systems where compact stellar remnants were consuming material from companion stars and releasing energy in powerful bursts, infrared detectors working at wavelengths just longer than visible light, using technologies that became available from the 1980s onward, could penetrate significantly deeper into the dust than optical instruments, and allowed astronomers to see stars, gas clouds, and structures in the central region that were completely invisible in the optical. Gamma-ray space telescopes, operating from the first decade of the 2000s with instruments like Integral and then Fermi, opened the highest energy window of all, detecting photons at energies millions of times greater than visible light. Photons produced by physical processes that ordinary stellar gas and normal dust clouds simply do not generate. Each wavelength regime revealed a different layer of what was happening at the galactic centre. Each instrument was looking at the same region of sky, but seeing a different physical component of an extraordinarily complex environment. The picture that assembled itself, observation by observation and decade by decade, was not what the models of the 1970s or 1980s or even 1990s had anticipated, not in scale, not in structure, not in the level of activity. To hold this in perspective, you need to feel the distance. Light, the fastest thing in the universe, travels at 299,792 kilometers per second in a vacuum. At that speed, it covers the distance from Earth to the Moon in 1.3 seconds. It crosses the diameter of the Sun in about 4.6 seconds. In 1 year, travelling constantly at that speed without pause, it covers approximately 9.46 trillion kilometres. Astronomers call that a light year, and it is the standard unit for measuring distances between stars and between galaxies. 26,000 light years. That is the distance from Earth to Sagittarius A. It means that every radio wave, every X-ray photon, every gamma-ray signal that arrives at our telescopes from the galactic centre today left its source 26,000 years ago. When those signals were emitted, the current form of our species, Homo sapiens anatomically modern, had already been walking the earth for roughly 80,000 years. But agriculture had not yet been invented. Writing systems did not exist. The domestication of animals was tens of thousands of years in the future. The oldest known cave paintings were being created in what would become France and Spain. The Pleistocene Ice Age was approaching its final maximum. Woolly mammoths still grazed across Eurasia and North America. We are not observing the galactic centre as it exists now. We are observing a 26,000-year-old snapshot of it. The anomalies we're about to examine, the unexpected structures and unexplained signals and mysterious energetic processes were already present at the galactic centre before a single permanent human settlement had ever been constructed anywhere on Earth. They are not recent. They are not transient. They are features of the galactic centre that have persisted across a time span longer than all of recorded human civilization by a factor of many. To feel the distance in a human frame, the New Horizons spacecraft, which reached Pluto in 2015 after 9.5 years of continuous flight, was moving at roughly 58,000 kilometers per hour. At that speed, reaching the galactic centre would take approximately 500 million years. 500 million years ago, complex multicellular life on Earth was still in its earlier stages. The first fish were not yet swimming. There was no grass, no forest, no land animal of any kind. That is the distance to the galactic centre, expressed in the only spacecraft speed we have ever actually achieved. Or express it differently. In the time it takes to sleep 8 hours tonight, a signal travelling at the speed of light covers about 8.6 light hours. At that rate, the signal takes 26,000 years to reach the galactic centre. In 26,000 years of sleep, at 8 hours per night, a person would sleep roughly 3.2 billion nights. The galactic centre is not merely distant in space. It is distant in a way that exceeds every scale we use to measure time and travel. And yet the galactic centre's output does not wait for our permission to propagate. It leaves when something produces it. It travels at whatever speed its nature permits. It arrives. The dust wall is not perfectly uniform across the sky. It has structural variations, regions where the intervening gas and dust columns are thinner, and where particular wavelengths of infrared or near-infrared light can penetrate more deeply before being completely absorbed. Astronomers have exploited these narrow windows with instruments of extraordinary precision. The gravity interferometer at the European Southern Observatory in Chile operates in the near-infrared and combines the light from 4 large telescopes simultaneously, achieving angular resolution equivalent to a telescope with a mirror over 100 meters across. It can track individual stars within the innermost fraction of a light-year of Sagittarius A, and measure their positions to an accuracy of a few tens of microarc seconds, about the apparent size of a golf ball on the surface of the Moon as seen from Earth. Using these instruments over spans of 2 and 3 decades, teams at the European Southern Observatory and at Keck Observatory in Hawaii have tracked dozens of individual stars in the galactic centre region, watching them move along their orbits around the central mass year by year. The orbits are ellipses. Their shapes, their periods, the velocities measured at different points along each orbit, all of it is consistent to extraordinary precision with what you would calculate if there were a compact mass of approximately 4.1 million solar masses concentrated at a single point in the centre of those orbits. That point is Sagittarius A. The black hole is confirmed not by seeing it, but by watching everything around it move in the only pattern consistent with its presence. And Sagittarius A is not the only thing at the centre. Sagittarius A contains 4 million suns compressed into a space smaller than Mercury's orbit. Sagittarius A sits at the bottom of a gravitational well, and around it, for hundreds of light years in every direction, the galactic centre environment extends. It is not an ordinary region of space. It is not even an extreme region of space by the modest standards of astrophysical extremity. It is categorically different from any environment within tens of thousands of light-years of our solar system, and understanding what happens there requires abandoning most of the intuitions built from studying the local neighbourhood. Begin with the stars immediately around the black hole. Within roughly 1/10 of a light-year of Sagittarius A, a region so small that it would fit within the distance between our Sun and Alpha Centauri, with room to spare, there exists a cluster of young, massive, hot stars. This is itself puzzling, because the tidal forces from a 4 million solar mass black hole at that distance should prevent the formation of stars in the conventional way. Gas clouds cannot collapse to form stars when the tidal shear from a nearby massive object is strong enough to tear them apart before gravity can pull them together. The young stars right next to Sagittarius AI should not, by standard star formation theory, be there. They are called the S-stars, and their existence is one of many problems the galactic centre poses to theorists. S2 is the most observed of them. Its orbit has been tracked continuously since the early 1990s, first by the European Southern Observatory team, and later by the Keck group as well. It is an elliptical orbit, as orbits under gravity must be. The ellipse is highly elongated, not nearly circular like Earth's orbit around the Sun. At its farthest point from Sagittarius N, S2 is roughly 10 times the Earth-Sun distance away, which would put it just inside the inner solar system if the Sun were replaced by Sagittarius A. At its closest approach, periapsis, S2 closes to about 120 Earth-Sun distances from the black hole. One orbit takes 16 years to complete, measured precisely from multiple successive periapsis passages. The speed at periapsis is what makes S2 famous in the community. At that closest approach, S2 moves at approximately 7,750 km per second. That is 2.555% of the speed of light. The Parker Solar Probe, which holds the human speed record for any spacecraft, reached 163 km per second during its closest solar pass, a number that captured headlines and required years of engineering to achieve. S2 moves 47 times faster than that, continuously, for the months around periapsis, not as an instantaneous peak, but as a sustained velocity during its closest orbital passage. At that speed, S2 would travel from Earth to the Sun in roughly 3.5 hours, from the Sun to Neptune, the outermost planet, in about a week. It would cross the entire Milky Way, at its narrowest, in about 4,000 years. It is a star doing that, not a particle, not a photon, a star with 15 times the mass of the Sun, physically larger than our Sun could ever be, swinging around the black hole at 2.555% the speed of light on a 16-year orbit. And it is a star doing this, not a particle, not a photon, a star with 15 times the mass of the Sun and a surface temperature of around 30,000 Kelvin, physically larger than our Sun could ever be, swinging around the black hole on a 16-year elliptical orbit at speeds that push against a few percent of the speed of light. The 2018 periapsis passage of S2 was observed by the gravity instrument with unprecedented precision. As S2 approached and then swung around its closest point, gravity measured something that S2 orbital observations had been looking for, but had not yet confirmed with this precision: gravitational redshift. The light from S2 at periapsis was shifted to longer wavelengths by exactly the amount predicted by general relativity for photons climbing out of the gravitational potential well near a 4 million solar mass object. The observation matched Einstein's 103-year-old prediction to within the measurement uncertainty. It was a direct test of general relativity in the strong gravitational field regime, conducted not in a laboratory but by watching a star orbit a black hole. Zoom out from the S-stars to encompass a region of a few light-years and you encounter the nuclear star cluster, the densest known stellar system in the Milky Way. It contains tens of millions of stars packed into a region, roughly 10 light-years across. The stellar density at its centre exceeds anything found in even the densest globular clusters. Stars there are, on average, separated by distances comparable to the outer solar system, rather than the light-years separating stars in our neighbourhood. Stellar collisions and close encounters that would be impossibly rare near the Sun become, on long time scales, occasional events. Extend outward to a few hundred light-years, and you reach the central molecular zone. This structure, roughly 1,000 light-years in diameter and perhaps 400 light-years thick, contains approximately 10% of all the molecular gas in the entire Milky Way, compressed into less than 1% of the galaxy's volume. Think about what the concentration means. The Milky Way contains several billion solar masses of molecular gas distributed across a disk 100,000 light-years in diameter. 1/10 of that total sits in a region that covers less than 1% of that disk's area. The gas density in the central molecular zone is orders of magnitude higher than the interstellar medium near the Sun. gas clouds that would expand and disperse in the sparse local neighbourhood are compressed and confined by the pressure of the surrounding environment. The magnetic fields threading through the central molecular zone are measured at roughly 100 to 1,000 times the strength of the interstellar magnetic field near the Sun. In our neighbourhood, the interstellar field runs at a few microgauss. At the galactic centre, measurements from polarization observations of dust and from Faraday rotation of radio sources behind the region indicate field strengths of hundreds of microgauss, approaching a milligauss in the most intense regions. Fields that strong do not merely carry magnetic flux passively through the medium. They organize the flow of gas, they channel the propagation of energetic particles, they control where shocks develop and how turbulence dissipates, and as we will see, they produce structures visible across hundreds of light years. The radiation environment has no local analogue. The massive young stars formed continuously in the central molecular zone over billions of years because the dense gas supply has never been fully depleted, pour out ultraviolet photons at rates that ionize surrounding gas across tens of light years per individual cluster. Dozens of such clusters are active simultaneously. Their combined ultraviolet output maintains a radiation field in the central molecular zone, roughly 1,000 times more intense than the average interstellar radiation field in the galactic disk. On top of that, the X-ray and gamma-ray flux from the black hole region, from supernova remnants, and from compact binary systems adds non-thermal radiation components that simply do not exist in comparable intensity anywhere in the outer galaxy. Astrophysicists who study starburst galaxies, distant systems where star formation rates are hundreds of times higher than our galaxy's current pace, use the central molecular zone as a nearby template. Because the conditions there, the gas density, radiation intensity, turbulence, magnetic field strength, are similar in kind to what must exist in those more extreme distant systems. The galactic centre is not just the centre of our galaxy, it is a local laboratory for astrophysical conditions that occur throughout the universe in more extreme form, accessible to us because it sits 26,000 light-years away rather than billions. Sagittarius A itself sits quietly at the bottom of all this activity, quiet by the standards of active galactic nuclei, meaning it is not currently producing the bright jets of radiation that characterize quasars and Seyfert galaxies observed at cosmological distances. But quiet is relative. Daily X-ray flares originate from the immediate environment of Sagittarius A, brief brightenings lasting hours caused by small amounts of material falling into the black hole's gravitational potential. The 2022 Event Horizon Telescope image resolved the shadow of Sagittarius A directly, showing a bright ring of hot gas surrounding a darker central region, exactly the structure predicted for the optically thick accretion flow around a black hole. The Event Horizon Telescope is not a single instrument. It is a planet-spanning array of radio telescopes working as a single, coherent interferometer, combining observations from facilities in Hawaii, Arizona, Chile, Spain, Greenland, Mexico, and Antarctica. The technique, called very long baseline interferometry, achieves an angular resolution proportional to the separation between the most widely spaced telescopes. With baselines extending nearly to the full diameter of Earth, the Event Horizon Telescope achieves angular resolution of roughly 20 micro-arc seconds, the apparent size of an orange on the surface of the Moon as seen from Earth. The Sagittarius A image required solving a challenge that the earlier M87 black hole image, released in 2019, did not face. M87's black hole is enormous, roughly 6.5 billion solar masses, and the gas orbiting it moves slowly enough that the image remains stable over the hours of observation. Sagittarius A is 4 million solar masses, with an event horizon roughly 1,500 times smaller in angular size on the sky. The gas orbiting it moves faster, completing orbits in minutes rather than days, which means the image was flickering and changing during the observation period. The team developed sophisticated imaging algorithms that could average over the temporal variability to produce a stable composite image. The result confirmed what decades of stellar orbit tracking had implied: a compact, massive object with an event horizon, approximately consistent with 4.1 million solar masses, surrounded by hot gas in circular motion, with a central shadow region where the black hole's gravity prevents light from escaping. The image is not a photograph of the black hole itself, which is by definition invisible. It is an image of the region around it, of the glowing gas that is falling in, heated to billions of degrees in the process. Understanding Sagittarius A, through its direct image, rather than inferring it entirely from stellar dynamics, provides a new tool for monitoring any changes in its accretion state. If Sagittarius A enters a more active phase in the future, the changes would be detectable first in the ring brightness, in the variability pattern of the flares, and in the radio emission from the accretion region. The violence at the centre is not what concerns scientists, it is what that violence is producing. In 2010, a telescope showed us two structures nobody knew existed, each one half the width of our entire galaxy. The Fermi Gamma Ray Space Telescope launched aboard a Delta II rocket on June 11, 2008. Its primary design purpose was systematic: conduct a continuous all-sky survey in gamma rays, cataloguing the diverse astrophysical population of gamma ray sources that previous instruments had detected at lower sensitivity, monitoring known sources for variability, and searching for signals of new physical processes, including the potential signatures of dark matter, particle annihilation that theoretical models had predicted might be detectable at gamma ray energies. The instrument itself, the Large Area Telescope, or LAT, was an engineering achievement. It could detect gamma-ray photons with energies from about 20 megaelectronvolts to more than 300 gigaelectronvolts, a range spanning 4 orders of magnitude. Its field of view covered roughly 20% of the sky at any given time, and in scanning mode it surveyed the entire sky every 3 hours. It was a general survey instrument designed for broad discovery, not optimized for any single target. Nobody planned specifically for what it found when analysts studied its data in the direction of the galactic center. In 2010, 2 years after Fermi's launch, a team led by Meng Su, Tracy Sleetier, and Douglas Finkbeiner, all at Harvard, published an analysis of the accumulated Fermi data in the direction of the galactic center. The analysis was methodologically careful and technically demanding. Producing a useful image of the galactic center region in gamma rays required building an accurate model of all the known contributions to the gamma ray sky in that direction. The emission from cosmic ray interactions with gas and dust in the galactic disk, the contributions from identified point sources, the isotropic background from extragalactic sources, and several other components. Only after subtracting all of these modelled contributions from the raw data could any residual signal be examined. The residual was not noise, it was not an instrumental artifact or a modelling error. The team checked it with multiple independent analysis approaches, using different data cuts, different background models, and different spatial analysis methods. The result was consistent across all of them. 2 enormous lobes of gamma-ray emission, one rising above the galactic plane and one extending below it, both centered symmetrically on the galactic center, each extending roughly 25,000 light-years perpendicular to the disk. Together, they spanned 50,000 light-years from the top of the upper lobe to the bottom of the lower one. The Milky Way's disk is approximately 100,000 light-years in diameter. These 2 structures together cover half the width of the galaxy from top to bottom, in a different direction. They are now called the Fermi bubbles. Before November 2010, the Fermi bubbles did not exist in any theoretical model of the Milky Way. No simulation of galactic evolution had predicted structures of that scale. No observational survey had suggested their existence. No theoretical framework had required them. They were completely absent from the scientific picture of our galaxy until the moment the Fermi data revealed them. Structures covering half the width of the galaxy, present and presumably having been present for millions of years, simply not known to exist until a space telescope found them. 6 to 8 million years ago is when the bubbles began forming. To anchor that number, 6 million years ago the lineages leading to modern humans and to modern chimpanzees had not yet diverged. Our ancestors were not yet walking upright in any consistent way. The first stone tools would not appear for another 2 million years. Whatever produced the Fermi bubbles was already inflating those structures before anything in our evolutionary line had learned to chip a rock. The fact that previous instruments had missed them is not as surprising as it might seem. The Fermi bubbles emit in gamma rays, a wavelength regime that requires space-based instrumentation because Earth's atmosphere is opaque to gamma rays. Previous gamma-ray space telescopes, CGRO, integral, had insufficient angular resolution or sensitivity to distinguish the faint, diffuse emission of the bubbles from the confused emission of the galactic plane and disk. Fermi's Lie had combined sufficient sensitivity with sufficient angular resolution to resolve the extended diffuse structure for the first time. The edges of the Fermi bubbles are sharper than you might expect from a cloud of gas expanding passively into a surrounding medium. A cloud expanding by thermal pressure alone would have a smooth gradient at its boundary, growing dimmer gradually as you move outward from the dense centre to the lower density periphery. The Fermi bubbles have boundaries that transition relatively abruptly from bright interior to dimmer exterior, implying a physical contact surface between the hotter, denser bubble interior and the cooler surrounding halo. This kind of sharp boundary is a feature of dynamics, of outflows pushing against a surrounding medium and creating a shell or shock at the interface. It is not a feature of passive, slowly expanding gas clouds. The age of the Fermi bubbles is estimated from the expansion rate. If you can measure how fast the bubble boundaries are moving outward, and you know how far they have travelled from the centre, you can calculate how long they have been expanding. Various measurements of the bubble expansion velocity, using different tracers at different wavelengths, have produced estimates in the range of 800 to 300 kilometers per second for the speed of the outflow driving the bubbles. At those speeds, growing from the galactic centre to a height of 25,000 light-years would require between 6 and 8 million years. 6 to 8 million years ago. That is a meaningful number. It falls within the geological period during which our hominin ancestors were diverging from the chimpanzee lineage. Early members of the genus Australopithecus were walking the African savanna at roughly that epoch. Whatever event produced the Fermi bubbles occurred in the galactic centre within the span of time that separates us from our non-human ancestors. The three competing explanations for the Fermi bubbles divide along lines that reflect the two primary ways a galaxy centre can produce large-scale energetic output. The first explanation involves Sagittarius A directly. Many supermassive black holes in other galaxies produce jets when they are actively accreting material. These jets are narrow, highly collimated streams of plasma and radiation, shooting outward from the poles of the rotating black hole system, perpendicular to the accretion disk. In radio galaxies observed at cosmological distances, these jets inflate enormous lobes of radio-emitting plasma that dwarf the host galaxy. The morphology, two lobes above and below the galactic plane centered on the active nucleus, is strikingly similar to the Fermi bubbles. The AGN jet hypothesis says Sagittarius A was in an active phase 6 to 8 million years ago, producing jets that inflated the bubbles and has since returned to its current quiet state as the accretion rate dropped. The second explanation invokes star formation rather than the black hole. The central molecular zone, the reservoir of dense gas surrounding the galactic center, is capable of sustained star formation. Massive stars born in the central molecular zone live only a few million years and then explode as supernovae. If the star formation rate in the central molecular zone was elevated 6 to 8 million years ago, producing many massive stars in a relatively concentrated period of time, the combined pressure from their supernova explosions could have driven a galactic wind. A wind from many distributed sources rather than a single jet would produce a broader, less collimated outflow, more consistent with the relatively smooth morphology of the Fermi bubbles, rather than the narrow lobes typically associated with AGN jets. The third explanation is dark matter annihilation, the same mechanism proposed for the galactic center gamma-ray excess that we will discuss in detail in the next section. The galactic center concentrates dark matter in its gravitational potential well, and if dark matter particles annihilate when they encounter one another, the gamma-ray output from that annihilation could be contributing to the bubble emission. Most researchers consider this a subdominant contribution at best for the large-scale bubble structure, but it has not been definitively ruled out. Beyond the three primary explanations, the physics of the Fermi bubbles presents a secondary puzzle, even within each model. Whatever mechanism created the bubbles had to inject an enormous amount of energy into the galactic center environment. Estimates of the total energy stored in the Fermi bubbles range from roughly 10 to the 54 ergs to 10 to the 55 ergs, where an erg is a unit of energy roughly equivalent to the kinetic energy of a flying mosquito. Those numbers are not intuitive, but a comparison makes them concrete. The Sun releases approximately 3.8 times 10 to the 33 ergs of energy per second. To accumulate 10 to the 54 ergs at the rate the Sun emits energy would take about 8 million years. In other words, the energy stored in the Fermi bubbles is equivalent to the total energy output of the Sun over the past 8 million years. But the Sun is an ordinary star. Sagittarius A, if active, would release energy at a rate billions of times higher. A star formation burst in the central molecular zone, with many stars exploding as supernovae, could also release comparable total energy over the relevant timescale. The energy budget of the Fermi bubbles does not uniquely distinguish between the two primary hypotheses. Both can supply the required energy in principle. What makes the energy budget discussion more interesting is the form of the energy. The Fermi bubbles emit primarily in gamma rays, specifically in the sub-gigahertz to tens of GeV range that Fermi's Large Area Telescope is optimized to detect. Gamma rays at those energies require either highly relativistic electrons producing inverse Compton, scattering off the cosmic microwave background photons, boosting those photons to gamma ray energies, or protons interacting with gas and producing pions that decay into gamma rays. These two emission mechanisms, called leptonic for the electron version and hadronic for the proton version, have different implications for what created the bubbles. Leptonic emission is more consistent with AGN jet scenarios, which can efficiently accelerate electrons. Hadronic emission is more consistent with starburst scenarios, which produce large numbers of cosmic ray protons through supernova shock acceleration. Measuring which dominates within the Fermi bubbles is technically difficult, because both mechanisms can produce similar gamma-ray spectra within the observational uncertainties of current instruments. Multi-wavelength observations have added detail without resolving the ambiguity. The Fermi bubbles have been detected in X-rays, in ultraviolet, and at radio wavelengths in addition to gamma rays, each tracer providing information about a different component of the bubble interior and boundary. The X-ray observations show a sharp edge at the bubble boundary, consistent with a contact surface between hot bubble gas and cooler surrounding halo gas. The ultraviolet observations show absorption features in the spectra of background galaxies seen through the bubble walls, revealing the kinematics of gas in the outflow at velocities of 800 to 1,300 kilometers per second. Radio observations constrain the magnetic field within the bubble interior. Each measurement narrows the range of viable models without eliminating the leading candidates. 15 years of analysis since the 2010 discovery, 3 candidate explanations, no confirmed mechanism. The Fermi bubbles are the largest known distinct structures associated with the Milky Way. They are almost certainly connected to the galactic center's past or current activity. And we do not know what made them. That fact alone would be enough to place the galactic center at the center of contemporary astrophysical research. But the Fermi bubbles are not the strangest thing found coming from there. Hundreds of light years long, perfectly aligned along magnetic field lines, and we have no idea what made them. Farhad Yousefzadeh published his first paper on galactic center radio filaments in 1984, based on observations taken with a very large array in New Mexico, then the most capable radio telescope array on Earth. The paper described thin, elongated radio-emitting structures in the galactic center region, extending for tens of light years, oriented predominantly perpendicular to the galactic plane, and emitting through synchrotron radiation rather than thermal processes. Synchrotron radiation is the key distinguishing feature. Thermal radio emission comes from gas at some temperature, with electrons bouncing around at speeds determined by that temperature and radiating as they do. The spectrum of thermal emission has a characteristic shape determined by the temperature. Synchrotron radiation comes from a completely different process. Electrons travelling at near-light speeds spiralling around magnetic field lines, curving in circles because the magnetic field deflects them, and emitting radiation as they curve. The spectrum of synchrotron radiation has a different characteristic shape, and the two can be distinguished observationally. Yousefzadeh found synchrotron-emitting filaments. This told him 3 things immediately. First, there were electrons in the galactic center region moving at near-light speed, requiring either a particle accelerator of some kind, or a recent injection of relativistic particles from some energetic event. Second, those electrons were confined within magnetic field lines for the length of the filament, meaning the magnetic field was strong enough and ordered enough over those length scales to maintain coherent structure across tens of light years. Third, the orientation of the filaments perpendicular to the galactic plane implied the magnetic field in the central molecular zone was not randomly tangled, as interstellar fields often are, but globally ordered in the vertical direction, threading upward and downward through the disk. At the time, only a handful of these filaments were catalogued. The radio telescopes of the 1980s lacked the sensitivity to detect the full population. What was visible was strange but manageable. A few dozen anomalous structures that theorists could attempt to explain with targeted models. What was not visible was the scale of the problem. The Meerkat Radio Telescope Array began science operations in 2018. Located in the Karoo Desert region of South Africa's Northern Cape Province, Meerkat consists of 64 dish antennas, working as a single interferometer. Its location in the southern hemisphere gives it a direct and favourable view of the galactic centre, which sits low in northern hemisphere skies, but passes nearly overhead from South Africa. Its design combines high sensitivity with the angular resolution to detect the faint diffuse emission from structures extended over several degrees on the sky. In 2022, Ian Haywood at the University of Oxford led the publication of a deep Meerkat image of the galactic centre region that revealed the filament population in its actual extent for the first time. The image, produced from 200 hours of observation processed with careful attention to avoiding imaging artifacts, showed not dozens of filaments but hundreds. extending across the full region covered by the image, some running in isolation, others appearing in parallel bundles of several strands separated by fractions of a light year from one another, individual filaments reaching lengths of 150 light years in some cases, running nearly perfectly straight across the image. The catalogue from the 2022 analysis contained over 900 individual filamentary structures, more than 10 times the number known from previous surveys. 900. To put a single filament in a human frame, one filament, 150 light-years long, running in a nearly perfect straight line, at the speed of sound, roughly 1,100 kilometers per hour, crossing 150 light-years would take over 130 billion years. That's about 9 times the current age of the universe. There are 900 of these structures in the galactic center region, all of them filled with electrons that are being continuously replenished, because synchrotron electrons radiate their energy away and go cold if nothing restores them. Something is feeding all 900 of them, continuously. All of them oriented the same way, perpendicular to the galactic plane. Every one of the 900-plus structures pointed in the same direction, consistent with the global magnetic field organization Yousefzadeh had inferred from the handful of filaments known in 1984. What was a local observation from a few structures had, with the full population visible, become a pervasive characteristic of the entire galactic center environment, and then in early 2023 the same team published a follow-up paper, a second population, running parallel to the galactic plane rather than perpendicular to it, oriented in the opposite direction relative to the disk, shorter and more compact than the perpendicular structures, associated with a specific large radio structure called the radio arc, one of the most prominent features in galactic center radio images, and spatially distinct from the perpendicular population while coexisting in the same general region. 2 populations of filaments, both made of relativistic electrons in organized magnetic fields, both in the galactic center, oriented at right angles to each other. If explaining the perpendicular population was already a substantial theoretical challenge, explaining 2 populations with orthogonal orientations in the same region requires a magnetic field structure of significantly more complexity than any existing model of the galactic center had incorporated. The electron acceleration problem is central to both populations. Electrons do not remain relativistic indefinitely. They lose energy as they radiate, through the synchrotron process itself and through other interactions. The timescale for a relativistic electron to lose half its energy to synchrotron radiation depends on the magnetic field strength and the initial electron energy. In the magnetic fields of the central molecular zone, that timescale is on the order of thousands to tens of thousands of years, which means the electrons in any given filament were accelerated recently on astrophysical timescales, not deposited billions of years ago and maintained since. Something is continuously producing relativistic electrons throughout the galactic center region, and injecting them into the magnetic field structures that form the filaments. The candidates are plausible but not confirmed. Pulsar wind nebulae are perhaps the most straightforward candidate. Pulsars, rapidly rotating neutron stars that emit beams of radio waves and a continuous wind of relativistic particles from their magnetospheres, are distributed throughout the galactic center region. The galactic center has hosted intense star formation over billions of years, and massive stars that explode as supernovae leave behind neutron stars. The pulsar wind inflates a surrounding nebula of synchrotron-emitting plasma, and in the presence of the organized magnetic field of the central molecular zone, that plasma could be channeled into filamentary structures aligned with the field lines. Magnetic reconnection provides another acceleration pathway. Reconnection events occur when magnetic field lines of opposite polarity are brought together by plasma motion and then snap into a new configuration, converting stored magnetic energy into particle kinetic energy. The turbulent, high-pressure environment of the central molecular zone generates the kind of plasma motions that drive reconnection. The energized particles then stream along the field lines, producing synchrotron radiation as they spiral. The galactic wind itself, the continuous outflow of material from the central region, could also be accelerating particles at the interface between the fast-moving outflow and the slower surrounding medium. Shocks at this interface would accelerate particles by Fermi acceleration, the process by which particles gain energy by bouncing between converging regions of compressed plasma. The same process produces the high-energy cosmic rays observed at Earth. 900 structures. Each mechanism accounts for some features but not all of them. The filaments exist. They are persistent. They are organized across the full extent of the galactic center region, and they do not yet have an agreed explanation. What the filaments tell us, regardless of which specific mechanism produced them, is that the galactic center is a more electrically active environment than any previous model had incorporated. Relativistic electrons exist throughout the central hundreds of light years in numbers and at energies that require continuous production. The magnetic field that organizes them into coherent filaments is globally ordered, not locally tangled, on scales of hundreds of light years, which is an organizational property that requires either a coherent source of magnetic flux or a process that has systematically aligned a chaotic field over time. The most significant implication is for the energy budget of the galactic center region. Maintaining a population of relativistic electrons at the densities implied by 900 synchrotron-emitting filaments requires a sustained power input. The electrons lose energy as they radiate, replace them faster than they lose energy, and the population is maintained. Stop replacing them, and the filaments go dark. The filaments are not dark, which means the power input is ongoing. Something at the galactic center is continuously accelerating electrons and distributing them along magnetic field lines throughout a region spanning hundreds of light years. That something is part of the same galactic center activity that produced the Fermi bubbles, the galactic wind, and the gamma-ray excess. It is not a separate anomaly. It is another face of the same underlying energetics, another measurement of the same central engine, seen at a different wavelength and a different spatial scale. Subscribe if you want to follow this as it develops. The section coming up involves the most hotly debated signal in modern astrophysics. 47 papers, 1 signal, 0 grid explanation. The galactic center gamma-ray excess was first identified in 2009, within the first year of Fermi telescope operations, by Lisa Goodenough and Dan Hooper, working at the Fermi National Accelerator Laboratory. It was not an obvious discovery. It required careful subtraction of the known contributions to the gamma-ray sky in the direction of the galactic center, the same kind of residual analysis that later produced the Fermi bubbles detection, and it emerged as a diffuse glow of gamma-ray emission concentrated around Sagittarius A. The excess had a set of characteristics that immediately drew the attention of particle physicists. It was spherically symmetric, meaning equally bright in all directions around the galactic center, rather than flattened into the disk. It had a radial profile matching the NFW profile, predicted by dark matter halo simulations, and its energy spectrum, the distribution of photon energies, matched the prediction for a specific type of dark matter particle. The dark matter particle in question is called a WIMP, a weakly interacting massive particle. WIMPs are the leading theoretical candidate for dark matter in many particle physics models. They interact through gravity and the weak nuclear force, but not through electromagnetism, which explains why they pass through ordinary matter without emitting light. They have masses in the range of tens to hundreds of gigaelectron volts. in the same range as the heaviest elementary particles detected at accelerators. And crucially for the gamma-ray excess story, they can annihilate when two WIMPs collide, producing standard model particles including bottom quarks that then decay into gamma rays. The energy spectrum of gamma rays produced by WIMP annihilation depends on the WIMP mass and the annihilation channel, the particular type of standard model particles produced in the annihilation. Theorists had calculated these spectra precisely for a range of WIMP parameters. The 2014 analysis by Dalen, Finkbeiner, Hooper, and collaborators compared the observed galactic center gamma-ray excess spectrum to these theoretical predictions, and found a match with WIMPs of mass roughly 31 to 40 giga-electron-volts, annihilating primarily into bottom quark pairs. The match was not marginal, it was good. Precise enough that the paper generated immediate excitement in the particle physics community, because it was consistent with WIMP dark matter parameters that were theoretically motivated from models beyond the standard model of particle physics, specifically from supersymmetric models. To understand the significance, consider what dark matter detection would mean. Dark matter is not a minor discrepancy in the galactic rotation data. It comprises approximately 27% of the total energy content of the observable universe. 5 times more than all the normal matter, all the atoms, all the stars, all the gas, all the planets, all the biological molecules in existence combined. We know it is there, know it has been there throughout cosmic history, know it shaped the formation of the first galaxies and the large-scale structure of the universe. But we have never detected a dark matter particle. Not with the most sensitive underground detectors, not with the most powerful colliders, not with any observation before this candidate signal. If the galactic center gamma-ray excess were confirmed as dark matter annihilation, it would be the first direct detection of the particle responsible for a quarter of the universe's energy content. It would be, without qualification, one of the most significant scientific discoveries in human history. The counter-proposals arrived quickly, because the particle physics community knows from experience that extraordinary claims require extraordinary scrutiny. The millisecond pulsar hypothesis was articulated by several groups within the following year. A millisecond pulsar is a neutron star rotating at hundreds of revolutions per second, spun up to those extreme rotation rates by accreting mass from a binary companion over billions of years. They are well-established gamma-ray emitters. The Fermi telescope has detected hundreds of individual millisecond pulsars throughout the Milky Way, and their gamma-ray spectra are characterized. A single millisecond pulsar produces a gamma-ray spectrum that, when convolved with realistic models for the distributions of pulsar spin periods and magnetic fields, can resemble the spectrum of WIMP annihilation in a particular mass range. The galactic center is expected to harbor a population of millisecond pulsars. The region has hosted intense stellar evolution for billions of years, creating many neutron stars. Binary star systems are common in dense stellar environments, and binary interactions can spin neutron stars up to millisecond periods. If the galactic center millisecond pulsar population is large enough, with hundreds to thousands of pulsars each individually too faint to be detected by Fermi as discrete sources, their combined emission could produce a diffuse gamma-ray excess with the characteristics observed. This is the crux of the problem. The two explanations, WIMP dark matter and a population of unresolved millisecond pulsars, produce nearly the same observable signature in the Fermi data. Both are spherically symmetric distributions. Both have energy spectra that can be made consistent with the observed excess. Both have radial profiles that can match the NFW profile. Distinguishing them from the gamma-ray data alone requires either resolving individual pulsars which the current Fermi instrument cannot do for faint sources at galactic center distances, or detecting subtle differences in the fine-grained spatial structure of the emission that lie at the edge of current statistical methods. 47 papers in the scientific literature have addressed this question directly as of 2024. They use a range of approaches: statistical tests for granularity in the emission that would indicate point sources versus a smooth dark matter distribution, multi-wavelength constraints from radio surveys that should detect individual pulses if they are present in sufficient numbers, theoretical modelling of the expected pulsar population based on stellar evolution models for the galactic center, cross-correlations with catalogues of X-ray sources, comparisons of the galactic center excess with similar excesses observed around other galaxies. Some analyses find statistical evidence of granularity consistent with an unresolved point source population. Others find the emission too smooth for the required pulsar numbers to be consistent with independent constraints on the pulsar population. Some radio surveys find fewer millisecond pulses in the galactic center than the pulsar hypothesis requires. Others argue the radio observations are affected by scattering in the dense ionized medium between us and the galactic center, which could hide a large pulsar population at radio wavelengths, while the pulsars remain visible in gamma rays. 47 papers, 1 signal, 0 agreed explanation. The signal is real. Its existence in the Fermi data is robust across independent analysis teams using different methods. What is not established is its origin, and the two origins it might have, a population of old stellar remnants or the first detection of the universe's missing matter, represent outcomes as different as any in modern physics. The stakes of the distinction deserve emphasis. If the excess comes from millisecond pulsars, the conclusion is that the galactic center contains a larger population of these objects than current stellar evolution models predicted, which is scientifically interesting and tells us something about star formation and neutron star physics in dense environments. It does not change our fundamental understanding of the universe. If the excess comes from dark matter annihilation, the conclusion is something else entirely. It means that the particle responsible for 27% of the energy content of the universe, the particle whose gravitational influence shaped the formation of the first galaxies and every galaxy since, the particle that has resisted direct detection for decades of increasingly sensitive experiments, finally revealed itself to a space telescope looking at the center of our own galaxy. It would tell us the WIMP mass, the annihilation cross-section, the primary decay channel. It would give particle physics its first confirmed signal of physics beyond the standard model from an astrophysical source. It would be among the most significant scientific discoveries since the confirmation of the Higgs boson at CERN in 2012, and arguably of greater cosmological significance. These two outcomes, one is a population statistics correction, and the other is the discovery of the century, cannot both be true simultaneously. The data right now supports both. That situation, where the evidence is genuinely consistent with two radically different realities, is not common in mature astrophysics. It is where the galactic center excess has sat for 15 years. The answer changes everything, and we still do not have it. Something at the center of the Milky Way is blowing hot gas outward at 1,000,000 kilometers per hour, and nobody agrees what is powering it. Galaxies are not closed systems. They exchange material with the space around them, accreting gas from their halos in the intergalactic medium, and also expelling material outward in large-scale winds and outflows. The study of galactic outflows is one of the most active areas in contemporary astrophysics, because these winds shape how galaxies evolve. They can quench star formation by expelling the gas that would otherwise collapse into new stars. They can enrich the circumgalactic medium with heavy elements synthesized inside the galaxy. They can regulate the mass of galaxies over cosmic time, and our galaxy has one. the Milky Way's galactic wind has been detected in multiple observational tracers across a range of wavelengths, each sensitive to a different temperature and density component of the outflow. At the hottest temperatures, millions of degrees, soft X-ray emission traces the most energetic component of the outflow. The Chandra X-ray Observatory and XMM Newton have both detected diffuse X-ray emission rising above and below the galactic center that is morphologically consistent with an outflowing hot gas component. At temperatures of millions of degrees, the gas emits primarily in X-rays and is too hot to radiate efficiently at longer wavelengths, making X-ray observations the primary tool for this component. At intermediate temperatures, tens of thousands of degrees, ultraviolet spectroscopy provides access to the outflow. When we observe background sources, quasars or other galaxies, through the line of sight toward the galactic center, their spectra show absorption lines from atoms and ions in the intervening gas. If that gas is moving toward or away from us, the absorption lines are Doppler shifted from their rest wavelengths. Systematic studies of these absorption features in the spectra of background sources at galactic longitudes corresponding to the galactic center direction show shifted absorption at velocities consistent with outflowing gas, providing a kinematic signature of the wind in this warmer component. At the coldest temperatures, well below the X-ray and UV regimes, radio observations detect dense neutral gas clouds being entrained in the hot wind. These clouds, which are too cold to produce X-ray or UV emission, become visible in radio observations of hydrogen emission lines. They are found at velocities above the normal rotation of the galactic disk, indicating they are moving outward from the galactic center rather than simply rotating with the rest of the galaxy. 3 temperature regimes, 3 observational techniques, the same outflow seen from different angles. Together they paint a picture of a structured multi-phase outflow originating from the galactic center and propagating outward through the halo. The velocities in the different components span a range. The cooler, denser clouds are being accelerated to a few hundred kilometers per second, swept up by the hotter, faster-moving medium around them. The hot X-ray emitting gas reaches velocities of 800 to 1,000 kilometers per second in some measurements. 1,000 kilometers per second is approximately 3.6 million kilometers per hour. The distance from Earth to the Moon in under 15 minutes. The solar system diameter in a few months. The mass outflow rate is substantial by galactic standards. The combination of all observed components, hot gas plus cooler entrained clouds, amounts to roughly 1 solar mass per year leaving the galactic center region. This is not material that disappears. It is material being moved from the galaxy's central reservoir into the halo, and potentially beyond. Over millions of years that accumulates to mass that would otherwise have been available for star formation in the galactic center. The Erizeta findings added a new dimension in 2020. Peter Pradale and the Erizeta team released the first all-sky X-ray survey at soft X-ray energies since the Rosat mission of the early 1990s, but with far greater sensitivity. The image of the galactic center region revealed 2 enormous structures of soft X-ray emission extending above and below the galactic plane, centered on the galactic center, reaching roughly 45,000 light-years in each direction. The Erizeta bubbles. Their relationship to the Fermi bubbles is immediately obvious morphologically and immediately ambiguous physically. Both are bilobe structures centered on the galactic center. Both extend perpendicular to the disk. The Fermi bubbles trace gamma-ray emission from high-energy electrons. The Erizeta bubbles trace soft X-ray emission from hot gas. They are not the same thing seen in 2 wavelengths. They are physically distinct structures, different temperatures, different emission mechanisms, different but overlapping spatial extents. The Erizeta bubbles are larger than the Fermi bubbles. If both were created by the same event, The Rosetta bubbles extending farther might indicate they were driven by an earlier phase of the same outflow, with the Fermi bubbles being a more recent, more energetic inner structure. Alternatively, they might have been created by separate events at different times, with the Rosetta bubbles being the older remnant of an earlier galactic center outburst, and the Fermi bubbles being a more recent one. Or they might represent physically distinct components of the same ongoing outflow at different temperatures, with the hotter E-Rosetta emitting gas at the outer shock and the cooler Fermi emitting electrons in the interior. All three interpretations have been published. None has been confirmed. What can be said with confidence is the scale. 90,000 light-years, the total height of the Rosetta bubbles from top to bottom, is 90% of the diameter of the Milky Way's disk. The structures coming out of the galactic center, both the Fermi bubbles and the Rosetta bubbles, and the galactic wind that continues driving them, are not compact features visible only near the galactic center. They are among the largest coherent structures associated with the Milky Way. They extend into the halo above and below the disk, into the diffuse gas that surrounds the galaxy's flat structure, and they are not historical relics. The galactic wind continues. The outflow is ongoing. In the time it takes you to sleep 8 hours tonight, the galactic center will have expelled roughly 46 kilograms of gas per second through this wind. In a single human lifetime of 80 years, that accumulates to roughly 2.5 times the mass of our Sun expelled outward into the halo. Over the span of all recorded human civilization 5,000 years, the equivalent of 5,000 suns worth of material has been moved from the galactic center into intergalactic space. While every human civilization that has ever existed rose and fell, the galactic wind did not pause once. The galaxy is not a stable machine. It breathes. The galaxy is not a stable machine. It breathes. 2 million years ago, Sagittarius A fired a beam of radiation powerful enough to ionize a structure 200,000 light-years away. The current Sagittarius A is quiet. By the standards of supermassive black holes, it is nearly dormant. Its total electromagnetic luminosity in the current epoch is roughly 40 solar luminosities, which sounds like a lot until you compare it to the luminosity of an active galactic nucleus, which can be 1 trillion solar luminosities or more, a factor of 25 billion times higher. Sagittarius A is emitting at a tiny fraction of what a black hole its mass could radiate if it were actively accreting material at a high rate. If you observed the Milky Way from another galaxy and tried to identify whether it had an active nucleus, the current emission from Sagittarius A would not flag it as active or unusual. But quiet is a present tense description applied to a system that has billions of years of history, and that history is written in the structures around it. The evidence for past activity at Sagittarius A comes from multiple independent observational approaches, all pointing toward the same conclusion. The galactic center was substantially more energetic in the relatively recent past, within the last few million years, than it is today. The evidence is not inferential or based on theoretical expectations. It is direct, observational, and in some cases quantitatively precise. The most striking piece involves the Magellanic Stream. The Magellanic Stream is a ribbon of neutral hydrogen gas arcing across roughly 200 degrees of the southern sky, trailing behind the large and small Magellanic Clouds as they orbit the Milky Way on an inbound trajectory that will eventually bring them into the main body of the galaxy. The stream was pulled out of the Magellanic Clouds by tidal forces during a past close pass of those dwarf galaxies by the Milky Way, and it now stretches through the outer halo at distances ranging from roughly 50,000 to 200,000 light-years from the galactic center. The Magellanic Stream was known for decades before anyone noticed that parts of it were ionized. Neutral hydrogen emits radio waves at the 21 centimeter wavelength, the most studied spectral line in radio astronomy, and surveys of the stream in this line had mapped it in detail. But ultraviolet spectroscopy of background sources seen through the stream, observations possible only from space because the atmosphere blocks UV, revealed something the radio surveys could not see. Some regions of the stream contained ionized hydrogen, meaning that the hydrogen atoms had lost their electrons to an external source of ionizing radiation. Ionizing radiation at the levels inferred from the stream's emission was incompatible with any known current source of UV or X-rays in the vicinity. The Magellanic Clouds themselves do not produce enough ionizing photons to account for the observed ionization at those distances. The diffuse extragalactic UV background is too faint. There was no current source capable of explaining what was observed. Jos Bland Hawthorne, at the time at the University of Sydney, published in 2013 the first quantitative analysis of the Magellanic Stream ionization that seriously considered the galactic centre as the source. The analysis modelled a past energetic event at Sagittarius A year, a Seyfert flare, borrowing the terminology for the kind of energetic activity seen in Seyfert galaxies where the central black hole is consuming material at an elevated rate. The model required the flare to have occurred approximately 2 million years ago, and to have produced ionizing radiation bright enough that, even attenuated by distance, it could ionize the hydrogen in the stream at its maximum distance of 200,000 light years. The geometry matters. The ionizing radiation would travel from Sagittarius A outward in all directions. The portion of the Magellanic Stream visible from the galactic centre's perspective lies along a particular direction. The model required that the ionizing radiation cone from the flare intersected the stream, which constrains the geometry of the hypothetical jet or outflow from Sagittarius A. When Bland Hawthorne and collaborators ran the numbers, including updates to the analysis in 2019, as better UV data on the stream became available, they found that the required flare luminosity was approximately consistent with Sagittarius A, having briefly operated as a low-luminosity Seyfert galaxy. 2 million years ago, an event at the galactic centre powerful enough to ionize gas 200,000 light-years away. Our ancestors, the early Homo lineage, the beings from which we descend directly, were alive at that time, walking upright across the African savannah, making and using stone tools, possibly communicating with rudimentary vocalizations that would one day become language. They watched the band of the Milky Way arc across their sky at night, not knowing that 26,000 light-years away, the centre of that band had recently concluded an energetic episode powerful enough to affect structures across the full extent of the galaxy's outer halo. They would not have seen it. The dust between us and the galactic centre hid Sagittarius A, then just as it hides it now. But the ionized hydrogen in the Magellanic Stream is the residual signature of that event, still present 2 million years later, still measurable with ultraviolet spectroscopes on space observatories, still offering evidence of what the galactic centre was doing when our ancestors were learning to chip flint. The X-ray light echo evidence provides a second independent confirmation of past galactic centre activity. In the molecular clouds surrounding the galactic centre, within a few hundred light-years of Sagittarius Aeris, X-ray emission has been detected that is too bright and too structured to be produced by the current low activity level of the black hole. The clouds are reflecting past X-ray emission from Sagittarius A, the way a mirror reflects light, a process called X-ray light echo, because the clouds are re-emitting light from a past source that has since dimmed. By tracking how the position of the brightest X-ray reflection has moved from cloud to cloud across multiple years of Chandra observations, the team studying these echoes can in principle reconstruct the trajectory of the reflected wavefront and thereby infer when the original X-ray flare occurred and how bright it was. The measurements are technically challenging, and the results span a range of inferred timescales for different cloud positions, but the general picture emerging is of an elevated X-ray luminosity from Sagittarius A within the last few hundred to few thousand years for one episode, and potentially a longer-lasting period of higher activity in the million-year range consistent with the Magellanic Stream evidence. The galactic centre has not been in its current quiet state throughout the past. It has been through active phases. It may be between them now. What would the Seyfert flare have looked like from Earth if it had been visible? The flare occurred 2 million years ago, so by definition its light reached Earth 2 million years ago, and any observer then with the right instruments would have seen it at that time. But working through the numbers is useful for grasping the energy scale. A Seyfert nucleus radiates at roughly 10 to the power of 44 ergs per second, a number that requires translation into human terms. The Sun radiates at about 3.8 times 10 to the power of 33 ergs per second. A Seyfert nucleus radiates at a rate about 10 billion times greater than the Sun. At the distance of 26,000 light-years, even that enormous luminosity would appear, to an observer without a telescope, as a point source. The dust would still block optical light, but an observer with UV and X-ray instruments would have detected a significant brightening in the direction of Sagittarius. From the perspective of impact, what Bland-Hawthorne's model implies is that the ionizing radiation cone from the flare was not a narrow beam. Seyfert galaxy ionization cones typically open to angles of tens of degrees. At the distance of the Magellanic Stream, a cone of that opening angle would illuminate a very large swath of the outer halo. The specific pattern of ionized and unionized regions within the Magellanic Stream constrains the geometry of the cone, and those constraints are consistent with what we observe in active Seyfert galaxies. The galactic centre, in its past active phase, appears to have been morphologically similar to those objects, just smaller in absolute luminosity and now cooled back to quiescence. The cooling timescale is itself informative. Seyfert activity is known to be episodic in other galaxies. Black holes cycle through active and quiescent phases on timescales of millions to tens of millions of years, depending on the fuel supply and on feedback mechanisms that regulate how much gas reaches the central region. Sagittarius A appears to have been in a low state for the past 2 million years, which places its current quiescence within the range of typical inter-episode quiet periods seen in other Seyfert-type nuclei. This does not make a future active episode imminent in any human-relevant sense, but it removes the assumption that Sagittarius A's current quiescence is a permanent feature rather than a phase in a longer cycle. The X-ray light echo evidence provides a second independent confirmation of past galactic centre activity. In the molecular clouds surrounding the galactic centre, within a few hundred light-years of Sagittarius A, X-ray emission has been detected that is too bright and too structured to be produced by the current low activity level of the black hole. The clouds are reflecting past X-ray emission from Sagittarius AE, the way a mirror reflects light, a process called X-ray light echo because the clouds are re-emitting light from a past source that has since dimmed. By tracking how the position of the brightest X-ray reflection has moved from cloud to cloud across multiple years of Chandra observations, the team studying these echoes can reconstruct when the original X-ray flare occurred and how bright it was. The measurements are technically challenging, but the picture emerging is of elevated X-ray luminosity from Sagittarius A within the last few 100,000 to few million years, consistent with the Magellanic Stream evidence. Two independent observational methods, both pointing at a period of elevated galactic centre activity within the last few million years, neither requiring the other, neither dependent on the same assumptions. The flare ended, but the structures it left behind did not. The galactic centre does not need to be dangerous to be consequential. It just needs to keep doing what it is already doing. Up to this point, the anomalies we have examined belong to the category of scientific puzzles with clean disciplinary ownership. The Fermi bubbles are an astrophysics problem. The X-ray filaments are a plasma physics and magnetic field problem. The gamma-ray excess is a particle physics problem with astrophysical implications. The galactic wind is a galactic evolution problem. Each belongs to a community of specialists who work on it, publish papers about it, and attend conferences to discuss it. But there is a second framing that changes the register of the conversation. Not what caused these anomalies, but what they are causing. Not what produced the Fermi bubbles, but what the Fermi bubbles and the processes that produced them are doing to the rest of the galaxy. Including the part of the galaxy where a small rocky planet orbits an ordinary star in a relatively quiet stretch of the Orion Arm, 26,000 light-years from the centre. You are downstream. This is not rhetorical emphasis. The solar system is embedded in the galactic disk, in the same continuous gas and magnetic field structure through which the galactic centre's outflow propagates, inside the same bubble of high-energy particles that the galactic centre's pevatron is continuously filling. The galactic wind does not stop at the boundary of the central molecular zone and wait politely for the outer disk to be out of the way. It propagates outward. The cosmic rays accelerated at the galactic centre do not remain localized to the central few hundred light-years. They propagate through the magnetic field of the galaxy, scattering on field irregularities, gradually diffusing outward from their source region. And eventually, after a propagation time that depends on their energy and the characteristics of the interstellar magnetic field, they arrive. Some of them arrive here. The cosmic ray connection is the most direct link between galactic center activity and Earth's environment. Cosmic rays are high-energy charged particles, primarily protons and heavier atomic nuclei, that arrive at Earth continuously from all directions in the sky. They were discovered in 1912 by Victor Hess, who flew electroscopes to high altitude in balloons and found that ionization increased with altitude rather than decreasing as expected if the ionizing radiation came from Earth's surface. Something was coming from above. It took decades to establish that the rays were actually particles, and more decades to begin understanding their sources and propagation. The cosmic ray energy spectrum covers an enormous range, from particles barely above thermal energies to particles with macroscopic kinetic energies, exceeding anything produced by human-made accelerators. The lower energy end of the spectrum is dominated by solar contributions, particles accelerated in solar flares and coronal mass ejections. The higher energy end, extending through energies of tera-electron volts and peta-electron volts and beyond, requires external galactic sources. The galactic center is one of the most plausible candidates for producing cosmic rays at the highest galactic energies. The evidence connecting the galactic center to high-energy cosmic ray production is observational. The Hess telescope array in Namibia, a ground-based instrument that detects the brief flashes of blue light produced in the upper atmosphere when high-energy gamma-ray photons or cosmic rays arrive, published in 2016 an analysis of very high-energy gamma-ray emission from the galactic center region. They detected diffuse gamma-ray emission extending over several degrees around the galactic center at energies up to tens of tera-electron volts, with a spectrum indicating the source was capable of accelerating protons to energies above 1 peta-electron volt. A peta-electron volt is 10 to the 15th electron volts. Compared to the Large Hadron Collider's maximum proton energy of 6.5 tera-electron volts, a peta-electron volt is about 150 times higher. Compared to the most energetic photons detected from the Sun, a PeV proton carries roughly 100 billion times more energy. The galactic center is doing naturally and continuously what our most ambitious engineering project can barely approach in controlled conditions for a fraction of a second. The Lhasa Observatory in Sichuan Province, China, is the most sensitive detector of ultra-high energy cosmic ray showers currently operating. Its 2023 publications identified gamma-ray sources emitting at energies extending above 100 peta-electron volts, including sources in the galactic center region, making them among the most energetic astrophysical emitters detected from galactic sources. These cosmic rays propagate through the galaxy. Their propagation is not direct, because they are electrically charged and the magnetic field of the galactic disk deflects their paths. They scatter on magnetic field irregularities, performing a random walk through the galaxy that can take millions of years to transport a particle from the galactic center to the outer disk. This randomization means that cosmic rays arriving at Earth carry no directional information about where they came from. They appear isotropic, coming from all directions equally, because the scattering has erased the source direction. But the flux, the total number of particles arriving per unit time per unit area, reflects the integrated output of all cosmic ray sources throughout the galaxy, weighted by source luminosity and distance. Some fraction of the cosmic ray flux at Earth originates from the galactic center, though the magnitude of that fraction is not precisely known and cannot be easily determined given the directional averaging from propagation. What changes when the galactic center becomes more active? The cosmic ray source strength at the galactic center increases. That increased output propagates outward. After the propagation delay, the cosmic ray flux throughout the galactic disk, including at Earth, increases modestly. The delay between an increase in galactic center activity and the corresponding increase in cosmic ray flux at Earth, for particles in the energy ranges most relevant for atmospheric ionization and surface biology, is estimated at roughly 1 to 10 million years, which means the Seyfert flare inferred 2 million years ago from the Magellanic Stream ionization, if it produced an enhanced cosmic ray output as active galactic nuclei in other galaxies are known to do, would be expected to produce an enhanced cosmic ray flux at Earth, somewhere between now and a few million years in the future. On human timescales, this is not detectable. On geological timescales, it becomes part of the environment. The cosmic ray flux at Earth affects atmospheric chemistry through ionization of the upper atmosphere, which influences the production of nitrogen oxides and other reactive species. It contributes to the total radiation dose received by living organisms, though at current flux levels this contribution is small compared to natural radioactivity from the Earth itself. At higher flux levels, sustained over geological timescales, the biological implications would be more significant. The atmospheric connection works through a chain of chemistry. High-energy cosmic rays entering the upper atmosphere collide with nitrogen and oxygen nuclei, producing secondary showers of particles including muons, electrons, and photons. Some of these secondaries reach the surface. At the shower level, the ionization produced by cosmic rays in the upper stratosphere affects the chemistry of ozone and nitrogen oxides. Elevated cosmic ray flux could modestly suppress stratospheric ozone at the latitude bands most exposed to the incoming primary particles. These effects are subtle at current background flux levels, but if the flux were elevated by a factor of several over geological timescales, the cumulative effect on surface ultraviolet dosing could become biologically meaningful. The cloud formation hypothesis, proposed by Henrik Svensmark and debated for decades in the climate science community, connects cosmic ray ionization in the lower troposphere to cloud nucleation rates. More ions from cosmic ray secondaries means more condensation nuclei means more low cloud cover means more reflected sunlight and a modest cooling effect. The hypothesis remains contested. Some observational studies find correlations between cosmic ray flux variations and cloud cover changes. Others find no statistically significant connection. The mechanism is physically plausible at the level of individual ion-induced nucleation events, but whether the effect is large enough to affect global cloud cover remains unresolved. The point is not that the galactic center is imminently going to alter Earth's climate or sterilize its surface. It is that the galactic center's output, in the form of cosmic rays, magnetic field flux, and energetic particles, is not disconnected from Earth's physical environment. It arrives here in amounts determined by the galactic center's activity level at the time of emission and by the propagation physics of the intervening medium. That arrival has been happening for billions of years. It is happening now. It will continue. This is not a threat assessment. The galactic center does not pose an imminent risk in any time frame relevant to human civilization. But on the timescales relevant to planetary habitability and to the deep history of life on Earth, the galactic center is not an external irrelevance. It is an environmental variable, one input among many into the conditions experienced by life on this planet over billions of years. None of this appears in current models of Earth habitability or of the drivers of mass extinction events. Given the observational evidence accumulated over the past 15 years for the galactic center's particle accelerating capabilities and for its past active phases, it may be worth incorporating. The galactic center does not need to be dangerous to be consequential. It just needs to keep doing what it is already doing. The word scientists use most often about the galactic center is not dangerous. It is unexpected. Scientific communication operates within a precise vocabulary that is often opaque to readers outside the field. The norms of academic publishing require restraint. Claims must be supported by evidence to a quantified statistical level before they can be stated. Conclusions must be bounded by their uncertainties. The language of certainty is reserved for things that have been definitively established through multiple independent confirmations. This means that scientific alarm, when it exists, does not read like alarm. It reads like the accumulation of carefully qualified statements in the results and discussion sections of papers in peer-reviewed journals. To understand what the galactic center literature is actually saying, you need to know how to read the register. Consider the language across the major findings of the past 15 years. The 2010 Fermi Bubbles paper by Su, Slatia and Finkbeiner states that the structures have no counterpart in any current model of the diffuse galactic gamma-ray emission, and that the total energy content of the bubbles, in the range of 10 to the 54 to 10 to the 55 ergs, challenges simple explanations and requires consideration of the galactic center's history. The phrase challenges simple explanations in a field where multiple explanations for observed phenomena are always available, means the explanations currently on offer are not adequate. The 2014 Dark Matter Excess paper by Dalen and collaborators states that the residual emission after subtraction of known contributions is robust against variations in the analysis methodology, and that a comprehensive search of existing gamma-ray source catalogues does not reveal any source population capable of accounting for the excess. When a paper says that a comprehensive search fails to find the source, it means the source is not among the things we currently understand. The 2022 Meerkat filament paper by Hayward and collaborators notes that the number of detected filaments substantially exceeds prior catalogues, and that the acceleration mechanism producing the relativistic electron populations remains an open question. When a paper uses the phrase open question about a phenomenon that has been studied for 40 years, it means the field does not have a satisfactory answer. The 2020 eRosita bubble paper by Predal and collaborators states that the relationship between the eRosita bubbles and the Fermi bubbles requires further observational and theoretical investigation, and that the driving mechanism for both structures is not yet established. Not yet established is scientific language for we do not know. Stack these statements from independent papers by independent teams using independent instruments across a 15-year period. Not one unexplained finding, not two. 6 separate major anomalies from the same region, each described in its own publication with its own careful qualifications, each individually contributing to a body of literature whose collective message is consistent. The Galactic Center is producing phenomena that current models do not fully account for, and the phenomena are real. That is the actual state of the science, not alarm, not panic. Something more precise and in some ways more significant than either. A systematic and growing recognition that the Galactic Center operates on scales, at energies, and in ways that the models built from studying the rest of the galaxy do not adequately describe. The response in the research community is not theoretical retreat. It is instrumental investment. The Cherenkov Telescope Array Observatory is the most concrete expression of that investment. CTAO is being built at 2 sites, Las Campanas Observatory in the Atacama Desert of northern Chile for the Southern Array, with access to the Galactic Center, and the Roque de los Muchachos Observatory on La Palma in the Canary Islands for the Northern Array. Each site will host a collection of telescope designs of different sizes optimized for different energy ranges. Large telescopes for the lowest gamma-ray energies, medium telescopes for the main energy range, and small telescopes for the highest energies. When complete, the combined CTAO system will have the sensitivity to detect gamma-ray sources roughly 10 times fainter than current instruments can detect, and angular resolution roughly 10 times better than Fermi for the relevant energy ranges. In the context of the Galactic Center science we have been discussing, CTAO is specifically designed to address the Galactic Center gamma-ray excess. Its sensitivity at the relevant energies and its angular resolution should be sufficient to distinguish between the dark matter and millisecond pulsar interpretations definitively. If the excess is from dark matter, CTAO should detect the characteristic spectral cutoff from WIMP annihilation at the WIMP mass. If it is from pulsars, CTAO should resolve individual bright pulses in the population and characterize the spatial granularity that diffuse dark matter would not show. CTAO's first light is expected in the late 2020s, with full science operations in the early 2030s. The Galactic Center is scheduled as one of its primary observing programs from the beginning. The next generation Very Large Array, in the planning stage with construction expected to begin in the late 2020s, will bring radio capabilities to the Galactic Center filament problem that current instruments, including Meerkat, cannot provide. With more than 10 times the collecting area of the current VLA and baselines extending to thousands of kilometers for the highest resolution observations, NGVLA would be able to resolve the internal structure of individual galactic center filaments, measuring how the synchrotron spectrum varies along a single filament's length, testing whether the acceleration mechanism is consistent with pulsars or reconnection or something else entirely. The Athena X-ray Observatory, currently in development at the European Space Agency with a targeted launch date in the early 2030s, represents the most significant advance in X-ray capabilities since Chandra, which launched in 1999. Athena carries an X-ray integral field unit spectrometer, capable of measuring the velocities, temperatures, and compositions of hot gas with spectral resolution more than 10 times better than any previous X-ray observatory. In the Galactic Center context, this means measuring the velocity field of the galactic wind with enough precision to map its 3-dimensional structure, test theories of what drives it, and understand how the Fermi and Erosista bubbles are connected to the ongoing outflow. 3 major observatories, under construction or in advanced development across 3 different wavelength regimes, all with the galactic center among their primary science targets. The investment represents the community's judgment that the galactic center anomalies are real, important, and tractable with better instruments. There is also work happening outside these flagship missions. The Square Kilometre Array, or SKA, currently being constructed in South Africa and Australia, will eventually surpass Meerkat's sensitivity by more than an order of magnitude. Its Galactic Center program will search for the individual millisecond pulses predicted by the pulsar hypothesis for the gamma-ray excess. If those pulses exist in the numbers required, SKA should detect them as individual radio sources. If SKA reaches its projected sensitivity and finds no such population, the pulsar hypothesis for the gamma-ray excess will be significantly weakened even before CTO returns its gamma-ray verdict. Ground-based gravitational wave detectors, LIGO in the United States and Virgo in Europe, are being upgraded through a series of observing runs that will eventually reach sensitivities capable of detecting the gravitational wave background from compact binary mergers throughout the galactic center region. Neutron star mergers in the galactic center's dense stellar population should produce detectable gravitational wave events, and the statistics of those events will constrain the compact object density in the central region, feeding into the models for both the pulsar excess hypothesis and the X-ray filament electron source problem. Radio pulsar timing arrays, experiments that use millisecond pulses distributed throughout the Milky Way as precision timing standards to detect very low-frequency gravitational waves, have recently reported evidence for a stochastic gravitational wave background in their data. The origin of this background is debated, with candidates ranging from supermassive black hole mergers in distant galaxies to cosmological sources from the early universe. If the background turns out to have a galactic center contribution related to the past activity of Sagittarius A, inferred from the Magellanic Stream and X-ray echo observations, it would add another line of evidence to the growing case for recent galactic center activity. Each of these instruments, across radio, X-ray, gamma-ray, and gravitational wave bands, is contributing a different facet to the picture of the galactic center. Each brings constraints that the others cannot, and each time a new generation of instruments has looked at the galactic center, it has found something the previous generation did not anticipate. This pattern of the galactic center consistently producing surprises as instrument sensitivity improves is itself a data point. It suggests the galactic center has not been fully characterized. It suggests the anomalies already found are not the complete catalogue of anomalies that exist. CTAO, Athena, NGVLA, and SKA will not deliver a final answer on the galactic center. They will deliver the next layer of surprises that the subsequent generation of instruments will need to explain. 6 anomalies, 1 source. The galactic center is not finished surprising us, but it is beginning to run low on places to hide. Subscribe so you're here when those answers come in. The next decade of galactic center research is going to be among the most significant in modern astrophysics. We started with a premise. The galactic center is too far away to matter, 26,000 light years, a number that stops meaning anything, a number that makes concern feel like an overreaction, like someone worrying about an event happening on the other side of the planet when there are immediate things to attend to. That premise is what the data has spent 15 years dismantling. The Fermi bubbles are 25,000 light-years tall above the disk, and 25,000 below, still expanding, still drawing energy from whatever source inflated them 6 to 8 million years ago. The Erecita bubbles are larger still, extending 45,000 light-years above and below the plane, filling the galactic halo with hot gas that did not exist in any pre-2020 model of the Milky Way. The galactic wind carries the equivalent of one solar mass of material outward from the galactic center every year, carrying with it the magnetic flux, the energetic particles, and the heavy elements that the central region has produced. The X-ray filaments thread through hundreds of light-years of the central molecular zone in organized structures whose electron populations were accelerated within the last few thousand to few 100,000 years, meaning the acceleration is ongoing, not historical. The galactic center gamma-ray excess glows at the very core, resisting 47 different attempts at explanation, possibly representing the first detection of the particle that makes up a quarter of the universe's energy content. And 2 million years ago, Sagittarius A produced an ionizing radiation event powerful enough to leave a measurable signature in a structure 200,000 light-years away. None of this stayed at the galactic center. None of it was contained by distance or by the dynamics of the central region alone. The Fermi and Rosetta bubbles extend into the halo above and below the disk where we live, structures that are not centered somewhere else but are part of the three-dimensional space our galaxy inhabits. The galactic wind is propagating through the same interstellar medium that the solar system moves through. The cosmic rays accelerated at PeV energies in the galactic center are scattered through the galaxy's magnetic field, and some fraction arrive at Earth, contributing to the radiation environment that life here has always experienced. You're not looking at the galactic center from the outside. You're embedded in the downstream of it, in the galaxy it anchors, breathing the same interstellar environment that its outflow has shaped over millions of years. The 26,000 light-years is not a safe distance. It is the travel time for the signals, the particles, the radiation, the outflows that have been leaving the galactic center since long before the first human being ever looked upward. The distance was never a wall, it was delay. What leaves the galactic center propagates outward on its own timescale. The Fermi bubbles took millions of years to grow. The flare that ionized the Magellanic Stream took 200,000 years for its leading edge to reach 200,000 light-years. The cosmic rays from the galactic center pevotron take millions of years to diffuse through the interstellar magnetic field before some fraction arrive at the inner solar system. Nothing leaves the galactic center and disappears. It arrives somewhere eventually. The anomalies are still accumulating. The filament catalogue from Meerkat grows as more data is processed. The gamma-ray excess analysis continues in parallel research groups. The Rosetta bubbles are being mapped at higher resolution with follow-up observations. The light echo evidence from molecular clouds near Sagittarius A is being updated with each new year of Chandra data. Each new result adds another layer to the picture of a galactic center that is more active, more structured, and more consequential for the rest of the galaxy than the models built before these instruments existed had suggested. The next decade will deliver answers. CTO will resolve the gamma-ray excess one way or the other, either confirming dark matter or establishing the millisecond pulsar population definitively enough to close the debate. Athena will map the galactic wind with a velocity precision that will constrain its driving mechanism. The NGVLA will probe the internal structure of individual filaments. The results will be significant regardless of which explanation turns out to be correct, because the explanations on offer are among the most consequential possibilities in contemporary physics. What will not change, regardless of how the specific questions resolve, is the underlying finding of 15 years of observation. The galactic center is not the passive, distant, irrelevant object that distance might suggest. It is the most energetic, most complex, most active part of the galaxy we inhabit. It has been shaping the Milky Way's structure and environment for billions of years and continues to do so. The anomalies are not the exception to a quiet, stable system. They are the signatures of a center that has always been doing this, and that we are only now beginning to see clearly enough to understand. 2 million years ago, Sagittarius A fired a cone of radiation powerful enough to reach the Magellanic Stream at 200,000 light-years. 6 to 8 million years ago, something at the galactic center inflated 2 lobes of gamma-ray emitting gas to half the width of the galaxy. 900 X-ray filaments, organized along magnetic field lines, are being continuously replenished by a particle accelerator whose identity is unknown. One gamma-ray signal at the very core either represents the universe's missing matter or a population of dead stars we cannot individually resolve. The galactic wind carries mass equivalent to a star per year outward from the center continuously. None of these things are happening somewhere else. They are happening in the galaxy we live in, produced by the center that anchors it, propagating through the medium we are embedded in. The 26,000 light-years that once seemed like an insulating distance is, from this perspective, simply the radius of our downstream position. We are not observers watching something happen at a safe remove. We are inside the system. The center is not silent.